You know, some of the most well-architected systems I've ever worked on were also a total nightmare to debug. On paper, everything looks perfect, right? You've got clean abstractions, interfaces everywhere, this beautiful separation of concerns. But then you get into production, and suddenly the simplest questions become incredibly expensive to answer.
And you're just staring at your screen asking yourself, where is this concrete implementation actually coming from? Why is this specific version being used right here? What is actually happening when a single request flows through this maze? Dependency injection is supposed to make our code cleaner, more flexible, easier to test, but a lot of the time, it does something else entirely.
And that right there is the heart of the problem. It hides what the code is actually doing behind all these layers of indirection. And once that starts to happen, clarity, the one thing you desperately need when something goes wrong at 3 a.m., just begins to quietly but consistently fade away. So let's dig into this.
This all leads to a scenario that I think is pretty familiar for a lot of us, where that theoretically perfect architecture ends up creating some very real and very frustrating problems when it hits the real world. I mean, the blueprint itself is flawless. The system is designed for maximum flexibility. You can swap out components, you can mock every dependency for your tests. Everything is just so neatly decoupled. This is the ideal we're all taught to aim for, right?
But then reality hits. An issue pops up in production, and that beautiful abstraction suddenly becomes a liability. The hunt to trace a single request through the system turns into this deep-sea dive through config files and modules and runtime bindings. All of a sudden, the cost of answering a simple question just skyrockets.
Okay, so if it can cause all these problems, why is dependency injection treated like this unquestioned golden rule in our industry? Well, to be fair, its reputation is built on some pretty solid foundations. And we all know the accepted benefits, right? It makes testing way easier because we can just inject mocks, it helps enforce loose coupling, it lines up perfectly with solid principles, and lets us swap out implementations without ever touching our core business logic. Plus, with modern frameworks, it all feels kind of magical and effortless.
Now, what's really interesting is where this way of thinking really took hold. It mostly comes from these big enterprise environments, where you've got massive teams working on incredibly complex systems. In that context, DI provided this crucial architectural discipline. It was a standard way to manage dependencies and coordinate the work of hundreds of engineers. It became the default, not just another pattern.
So what happened? Well, the entire industry started to optimize for the flexibility and the scalability of teams and these huge pluggable systems. And for the problems they were solving back then, that was a totally rational choice. But that optimization wasn't free. It came with a whole set of hidden costs and trade-offs that we often just forget to talk about.
So let's pull back the curtain on what I call the architectural tax. These are the subtle compounding costs that we pay when we just apply dependency injection as a default for everything, instead of using it as a specific tool for a specific job. This is a huge one. Overusing DI absolutely breaks a crucial property of understandable code, local reasoning. The moment you can no longer understand what a file does just by reading it, because its most important dependencies are magically injected from somewhere else entirely, you've lost. You now need to understand the entire DI container just to understand a single module. And this just perfectly illustrates that indirection I was talking about. To understand one simple request, you're not reading code linearly anymore. Nope, you're jumping all over the place. A method gets called, then the framework has to resolve an interface, then the DI container has to go find the right binding, then it instantiates the object, and only then, finally, does your business logic actually run. Debugging this isn't just complex, it's painfully slow.
This leads to a symptom that I'm sure we've all seen, something called constructor explosion. You open up a class and see a single service that needs 5, 10, maybe even 15 dependencies injected into its constructor just to work. Now, each one might represent a single tiny responsibility, but the end result isn't simplicity, it's just fragmentation. And it makes that class incredibly difficult to work with.
And these costs, they're not theoretical, they absolutely compound. At runtime, all these extra objects that need to be created and managed mean more memory usage and more work for the garbage collector. Performance takes a real hit, especially with slower cold starts in serverless environments. The cognitive load on you, the developer, is huge. And maybe the most painful part? A simple typo in a configuration file somewhere can lead to this mysterious runtime failure, instead of a nice, clear error from your compiler.
So this brings us to the central trade-off that I think experienced engineers are navigating every single day. It's not about whether a pattern is good or bad in a textbook. It's about weighing the real-world costs. And that brings us to this core conflict: flexibility versus clarity.
On one side, you've got the theory, a system that's optimized for flexibility. It hides dependencies, but it's much harder to trace. On the other side, you've got the reality of production, a system that's optimized for clarity. It reveals its dependencies right there in the open, and it's so much easier to debug when things inevitably go wrong.
Look, senior engineers don't evaluate decisions based on buzzwords. They think in terms of a cost model. Every single architectural decision adds latency or memory usage or CPU overhead. It adds cognitive load for the next developer who has to work on it. It increases debugging complexity and operational risk. Flexibility is just one item on this list, and honestly, it's not always the most important one. And the truth is, in many common scenarios, like stable, small to medium-sized services, the math is actually pretty simple. Explicitness wins. A direct import statement is faster to read and trace. Explicitly creating an object with new is easier to debug. You don't need to understand a whole complicated container just to understand the system.
So, where does that leave us? What should we really be optimizing for? I think it's time we shift our focus away from blindly applying patterns and start cultivating some practical virtues in our architecture. And this, for me, is the real light bulb moment. We spend so much energy fighting this boogeyman of tight coupling, but the vast majority of bugs in production, they don't come from that. They come from systems where the behavior is just plain unclear. We've been optimizing against the wrong enemy. Instead, let's focus on these things. Make dependencies explicit so they're easy to reason about. Make sure that data flow is clear to reduce debugging time. Use simple object construction to reduce failure points. Keep that heavy indirection out of our performance-critical paths. And maybe most importantly, measure the actual need for abstraction before you build it for a future you might never have.
So here's the big takeaway, and it might sound a little controversial, but I think it's deeply true. For many real-world systems, clarity is the thing that scales best. Better than abstraction, better than flexibility. A system that the whole team can actually understand is a system they can maintain and evolve effectively for years. At the end of the day, maybe we need to redefine our goal. Good architecture isn't about collecting a checklist of design patterns. It's about a single, practical mission, making our systems easier for a human being to understand, especially when they inevitably fail. So I'll just leave you with this question. Take a hard look at the systems you're building today. Are you adding all this complexity to optimize for some hypothetical, flexible future that might never even happen? Or are you optimizing for clarity, to make sure that when a real failure occurs, you and your team will actually be able to figure it out and fix it?